In this video, we are going to be looking at some of the topics that will be on OCR paper 1, namely mechanics, the SHM circular motion, and even some cosmology stuff. So in this video, I've created a sort of a study where we're going to look at different aspects in the same scenario. So this scenario is the physics of getaway driving. So you're in charge of making a getaway from a bank robbery. The getaway vehicle is going to be a transit van, classic getaway vehicle. And we've got some dimensions, and we can see where the object center of mass is as well. And we can see that initially, anyway, it's got a mass of 5,000 kilograms. Okay, so that's our starting point. So each wheel has a spring as part of its suspension system. If all the springs are identical, explain which springs will be most compressed if the center of mass is as shown on the diagram and it's traveling at constant speed of 100 kilometers per hour. So because it's a constant speed, it's in equilibrium, which means we can apply the principle of moments. So we take moments about the center of mass. The distance from the center of mass to the front wheel is 1.7. The distance from the center of mass to the back wheel is 1.1. So if those two expressions are equal to each other, we can see that the force at the back has to be bigger as its perpendicular distance is smaller. And because of that, the springs at the back must be most compressed because that's how they provide a bigger force. So that's how we know this one. Okay, so if each spring has a stiffness constant of 49 kilonewtons per meter, calculate the compression in each spring, which will be in the equilibrium position when traveling at constant speed. So, first of all, I'm going to take moments about the front wheels because I'm going to try and figure out the extension of or the compression of the back wheels. So we've got the weight force of the truck multiplied by the perpendicular distance from the front wheel, and we've got the springs at the back are 2.8 from the front wheel. There are 2 springs at the back, which is why it's multiplied by 2, and the spring constant is 49,000, and then we times it by the compression, rearrange, and we can find the compression at the back is 0.3 meters. You can take moments about the back wheels, essentially repeating the process, and we get a compression at the front is 0.20 meters. So we can see we've confirmed our answer from the previous question. So if the springs have a cross-sectional area of 100 centimeters squared and an unstretched length of 25 centimeters, calculate the Young modulus of the springs. So first off, Young modulus is stress over strain, which can be calculated doing force times the original length over the cross-section area times the extension or compression. So I'm going to rearrange that to make F the subject, and you'll notice that this now looks an awful lot like Hooke's law, where the spring constant has been replaced with EA over L. So that means spring constant is Young modulus times cross-sectional area divided by length. So if we want the Young modulus, we just need to multiply by length, divide by area. And remember to convert the area into meters squared. So 1 centimeter squared is 1/10,000th of a meter square. So that's why we've times by 10 to the minus 4, giving us a Young modulus of 1.2 times 10 to the 6 pascals. Okay, so we've worked out about the springs we'd need. Okay, so we're now on the getaway, and a policeman spots the van and suspects it is speeding, and they pull out a radar gun, which is kind of like a speed camera, and it shoots an infrared beam to the car, as we can see. So if the policeman is stationary and the frequency of the beam is 600 gigahertz, which is in the infrared spectrum, so that makes sense, calculate the frequency change of the infrared beam when it returns to the radar gun detector. So what we've got here is a Doppler effect question, and we've got a scenario where we've got reflection and we've got the beam traveling at an angle to the motion. So this is very like the ultrasound stuff in the final topic. But so we're going to use this form of the Doppler effect equation because it's being reflected. That's why it's multiplied by 2, and the the light and the object are traveling in different directions, which is why there's the cosine in there. We want the change in frequency, so we're just going to multiply both sides by f, plug the numbers in, and we end up with a frequency change of 9.6 times 10 to the 4 hertz. Okay, so you're approaching a checkpoint and are nervous because you have 2 hostages in the back of the van. We've just done a bank robbery. Why wouldn't we have hostages? And the police are obviously on the lookout for the bank robbers, and they're using an infrared camera to look at the contents of different vans. Explain why people look different to an infrared camera than the van. So, first of all, the key is the temperature of the people is going to be higher than the van. Most of the van will be at air temperature, so about 20 degrees. The people will be at 37 degrees. So according to Wien's displacement law, the wavelength of the radiation with the highest intensity from the people will be a shorter wavelength than the van. So that's how it would look to an infrared camera, and however they decide to put that on the screen. So as you approach the checkpoint, you drive over a speed bump that gives the springs of your suspension a displacement of 0.15 meters from their equilibrium position. If they oscillate with a time period of 0.23 seconds, calculate their displacement from the equilibrium position are the 2 seconds if they are undamped. So it's given an initial displacement and immediately starts oscillating. So we're going to use a cosine function to model the displacement. And then we know what the amplitude is, we know what the time period is, and we know what the time is. So we can calculate that in this case, it's going to be 0.05 or 5 centimeters below the equilibrium position. Okay, so in the last question, we dealt with undamped springs. In reality, the suspension springs are in tubes full of water, or sometimes even more viscous fluid than that. So why are they in that? Well, the reason is what we're trying to do is work against the motion of the object. So there's going to be a large drag force from water, and it's going to be much larger than it would be if it was just air. And that's going to act to decrease the mechanical energy of the spring system, which are the springs in the car and whatever. So because the amplitude squared is directly proportional to mechanical energy, so the water is effectively acting to decrease the amplitude of vibration, and it decreases it quicker in water than it would in air. So that's why it's put in, because we don't want to sit there going up and down all day. We want the oscillations to stop. Okay, so a policeman scans your van with the infrared camera and raises the alarm. So you have to make a quick getaway. So you push down the accelerator hard. This causes a rapid burning of fuel, which raises the temperature of the gas in the pistons of the engine from 800 degrees C to 1200 degrees C. If the pistons are sealed with a fixed volume, calculate the final pressure if they were initially at 10 times atmospheric pressure of that value. Okay, so if we have it's sealed, so that means the number of moles is fixed and the volume is fixed, we can use this expression here, also known as the pressure law. And then we want the final pressure, so we want to make P2 the subject, and we need to convert the temperatures into Kelvin, put the pressure in pascals, so 10 times 1.01 times 10 to the 5, and that gives us a final pressure of 1.4 times 10 to the 6 pascals. Okay. So explain in terms of the kinetic model of gases why the pressure rises. So all that's changed is the temperature has gone up. Okay, so the container is still a fixed volume. So when you raise the temperature, you raise the root mean square speed of gas particles, which means that the momentum change in each elastic collision with the container walls is bigger. And the other thing that happens is because they're traveling faster, you get more collisions per second, or they collide more frequently. And both of those two things act to increase the force on the container wall, essentially just using Newton's second law. So if the area is fixed, if the force is increasing, that would mean the pressure is going to be greater as well. Okay, so we're making a getaway. We've smashed into a barrier and it breaks the barrier. And the barrier is carried with the van at 140 kilometers per hour. So we're going pretty quickly now. If the barrier has a mass of 120 kilograms, calculate the impulse that acts on the van. Okay, so what I'm going to do is work out the impulse on the barrier, because that is going to be the same as the impulse on the van using Newton's third law. So the barrier is initially stationary, so it's increased its velocity to 140 kilometers per hour. Its mass is 120, so we get an impulse on the barrier of 4.7 kilonewton seconds, which will be the same as the impulse on the van. The barrier damages the radiator of the car, which is designed to cool the engine by pumping water. If the engine produces thermal energy at a rate of 7.5 kilowatts, calculate the volume of water that must pass through the engine per second if the water is only going to increase in temperature by 20 degrees. So we've got the specific heat capacity, we've got the density of water. So first of all, what we can do is the normal equation is Q equals mc delta T. So if we have the thermal energy per second and the mass per second, that's the same equation. We want the volume per second. So volume is mass is density times volume. And we want the volume per second, so we can rearrange to make that the subject and plug the values in. And we end up with a flow rate of 8.9 times 10 to the minus 5 meters cubed per second. So not a massive flow rate there. Okay, so the damage blocks the radiator and it's trapped 5.2 liters of water in the engine. But initially at 20 degrees C, calculate how long it would take to turn all of the water into gas and explode the engine. And we've got the specific latent heat of vaporization of water. Okay, so there are going to be two parts to this. Calculate how much energy it takes to raise the temperature to 100 degrees, and then work out the energy it takes to change the state. So we've got 5.2 liters. 1 liter is 1,000th of a meter cubed. So that's me converting it into meters cubed, times it by 1,000 turns it into a mass. Then we times it by the heat capacity and the temperature change. Likewise with the phase change, first of all, calculating what the mass is, so not bothering to divide by 1,000 and times by 1,000 again, and then we get the energy to change state, and when we add those together, we get a total energy, and if we divide that by the rate at which thermal energy is supplied, that gives us the time it would take, which is about half an hour. Okay, so traveling at a speed of 140 kilometers per hour, the van, with all its hostages, etc., has a total mass of 5,600. Calculate the frictional force at the wheels in order for the van to turn a corner with a radius of curvature of 200 meters. So this is a fairly simple circular motion question. We just need to make sure we convert the speed into meters per second, but otherwise fairly easy. So if the road is banked, so in this case with an angle of 15 degrees, explain why the van is able to travel faster. So to travel faster, you need a bigger centripetal force. So that must be the reason why. So in this case, the normal contact force from the road has a component towards the center of the circle in which it's traveling, which makes the centripetal force bigger. And because of that, if we have a fixed mass and a fixed radius of curvature, centripetal force is directly proportional to velocity squared. So if the force is bigger, the velocity can also be bigger. Okay. So having left the corner, the engine finally explodes and there's no longer any thrust to drive the van forwards. If the total resistive force has a constant value of 1,200 newtons, calculate how far the van can travel before it stops. So because the force is constant, we can use some suvat here. So first you can work out the acceleration. The final velocity is going to be 0, and then we just have to plug in the numbers, making sure it's in meters per second squared, giving us 3.5 kilometers. So it can travel quite far, but it was traveling quite fast to start with. In reality, is the distance likely to be greater or less than the value calculated in this question. Explain your reasoning. So I think it's going to be larger, mainly because the resistive force is going to get smaller. So as velocity decreases, drag force gets smaller, so that's going to make the magnitude of acceleration smaller, and so the distance traveled will be larger. Okay, so finally, your van grinds to a halt and you're surrounded by the police. You're arrested and taken straight to jail because, frankly, even in physics, crime doesn't pay. The police are going to get you. Sorry.